All right, well, we'll make a start because we have a lot to cover today. So welcome to today's webinar on alumina decarbonisation for the HILT CRC. My name is Rochelle Doyle and I'm the Program 1 lead for HILT. Today we're going to be providing an update on the AlumiNEXT project and also a broader discussion on the technologies and integration challenges that are facing the industry as we transition to low carbon alumina. So I'd just like to start by acknowledging the Whadjuk Noongar people, who are the traditional custodians of the land in Perth where I am today, and pay my respects to elders past and present. First Nation cultures have had a really long understood the knowledge that sharing is really powerful, and activities like what we're doing today are sort of meaning that same thing of ensuring that knowledge is shared. I'd also like to acknowledge the traditional owners on the lands where each of you is joining us from, which is quite a diverse group, and I extend that respect to other Aboriginal and Torres Strait Islanders who are with us today. So we have a pretty jam-packed agenda for our hour together. We'll be opening with Margie Johnson, who's the CEO of the Australian Alumina Council, giving us a broad overview of the challenges in the sector. Professor Gus Nathan, who's our CRC Research Director and also part of Adelaide Uni, will then share a technical perspective on the future of decarbonisation and how those emerging technologies will assist us in that. We'll move to Associate Professor Saw so that he can then give us an update on the specific AlumiNEXT projects and a bit of a deep dive into some of the findings to date. And then Emilio Pai from Emirates Global Aluminium is going to close out by sharing some specific perspectives from his industry. Once that's happened, we'll move to Q&A. Hopefully, we'll have enough time. You will see a Q&A button up in the top of your Teams function. If you could please enter your questions in there, that would be very much appreciated. So we have amazing speakers. As I said, I'm just going to call out one or two key facts from their bios so we can get going. So Margie's got 25 years experience in Australian mining and manufacturing sectors, and she's been a non-executive director on a number of boards, and is joining us today to give that overall industry perspective. Gus Nathan, who, as I mentioned, is our research director. He's led multiple different technology platform developments, instrumental in the creation of this CRC, and has a lot of involvement in the high temperature minerals processing space. So Associate Professor Saw, expert in high temperature reaction engineering, and you'll hear a lot about the expertise he's bringing to the table today, and the inventor of a patented net zero steam calcination technology, which is extremely exciting. And then we have Emilio, who's the Director of Process Engineering at Emirates Global Aluminium. He's got 26 years experience in the industry and specialises in energy, bauxite, refining and alumina production, and has had a number of technical roles across many of the companies that have formed part of the industry. And he's joining us today as one of our key industry participants in the AlumiNEXT project. So with that, I'm going to hand over to Margie and look forward to hearing the presentations and some interesting discussion. Thanks, Margie.
Worries. Thanks, Rochelle, and hopefully my Teams complies, but while it's thinking about it, I'm going to try and do a very high level presentation just to give you some context for the speakers who'll follow me. So first of all, a quick reminder of the vertically integrated aluminium chain that we have here in Australia. So we have 6 bauxite mines, predominantly in Northern Australia and Southwest WA. We have 5 alumina refineries, 4 aluminium smelters and more than 20 extrusion presses. We also help employ and put food on the table for more than 75,000 people, families predominantly in regional Australia. I'm sure it's not news to anyone on this in this meeting today, but a quick reminder that our refineries are located in Gladstone and Southwest WA. In terms of where we sit globally, aluminium is a really globally significant sector in terms of its global emissions. It's often considered the 3rd largest industrial sector in terms of emissions after steel and cement, and it's got over 1,000 million tonnes of carbon dioxide emissions every year. The International Aluminium Institute has done a lot of work at a sectoral level on their global pathways, and I really encourage you to look at their website to delve into that work more deeply. The primary aluminium production value chain from mine to market is energy intensive. More than 60% of the global aluminium sector's emissions come from the production of electricity. The major sources, so number 2 on their graphic, the major source of non-electricity related emissions in the sector are fuel combustion in alumina refineries and smelter anode combustion. And then the third, I guess, sort of non-emitting source, or much lower emission source, is recycling and resource efficiency. So infinite recyclability without loss of properties is one of aluminium's unique benefits. And globally, the recycling of post-consumer scrap today mitigates the need for more than 40 million tonnes of primary aluminium production every year. Globally, we've seen a lot of focus at a high level on Pathway 1, and we also have that here in Australia, obviously decarbonising our electricity. And we've also seen, particularly in Europe and North America and parts of South America, a really high focus on Pathway number 3, the recycling pathway. Inert anodes, which some of you may have heard about, form part of Pathway 2. But for alumina decarbonisation, that's really part of the global sector's Pathway 2. And it's an important part in terms of where Australia comes in. So Australia is the world's largest producer of alumina outside of China. So we're the world's second largest producer, and we're the largest exporter of alumina. We produce around 17 million tonnes of alumina a year, about 85% of which is exported, and 15% is turned into aluminium domestically. We have more than 60 years of technical experience in bauxite mining and alumina refining technologies. And this experience helps not only us, but also our customers across bauxite, alumina, and aluminium reach their sustainability goals. We also have the global research headquarters for alumina for Alcoa, Rio Tinto and South32's Wesleyan operations based here in Australia, which helps us develop new technologies as part of our global contribution. All our members are also involved in the HILT CRC and all involved in the AlumiNEXT project, which was discussed later and is a really important opportunity for collaboration. Our alumina is some of the world's lowest emissions alumina already as well. What you can see when you look at those graphics at the top is we're just under 3% of the global industry's emissions, but we're nearly 7% of national emissions, and hence the importance in Australia in terms of the focus we have. As Australia, most people, when they think of aluminium emissions, they really turn to the primary aluminium rather than alumina. But because we're a very large producer of alumina, it forms a large part of our industry's footprint in Australia. So it's around 12.6 million tonnes, and this is very recently released 2025 data, or just above 40% of our total emissions footprint here in Australia. I'm not going to try and explain the alumina process to the people on this call. You probably know an awful lot about that. But what I've included here is an extract from one of the fact sheets on our website where we outline what we think the emissions pathways and challenges are and give a bit of a high level ranking to these. It's important to note that around a third of the energy used in an alumina plant is for calcination and 2/3 is for digestion. In Australia, all our calcination is done using gas, and for digestion, it's a mixture of gas and coal, which is why the percentage emissions don't align quite with the energy percentage. So that chart on the right, what you can see is the main pathways are electrification, alternate energy, and hydrogen. Electrification is by far the biggest opportunity. On the other two, briefly, cogeneration plants can be co-fired on biomass. Despite it being technical feasibility, the volume of biomass in Australia is really the limiting thing. For hydrogen, we're certainly investigating the production and use of hydrogen, particularly for calcination, where the required temperatures are harder to achieve with electrification. The biggest challenges with electrification are, while we're talking two things. One, we're talking about inside the fence technology. So we have to figure out how to use electricity. Things that run on coal and gas today, how are we going to make them run on electricity tomorrow? But also outside the fence, we need availability of electricity. So the Australian Renewable Energy Agency estimated we'd need 3 to 5 gigawatts of new firmed, reliable supply to meet the industry. And don't forget that for firming, you need to multiply that 3 to 5 gigawatts by another 3 to 4. So it makes a pretty big number. Electrification of the refineries would materially impact the total grid demand. So a large electrified alumina refinery is about the same size as a smelter, so around a gigawatt or so of electricity. And in the regions in which we operate, not only is it material, but we don't traditionally have substantial transmission infrastructure running to our alumina refineries, and that's a big challenge. One opportunity, though, really is thermal storage, particularly as an enabling technology in terms of how we can provide refineries with greater flexibility to reduce the grid imports during periods of high pricing or lack of generation capacity. And that would help the refineries to sustain their operation and improve the overall business case, mitigating some of the uncertainty. So how we electrify will be important. So as I said, super quick snapshot. I will hand over to Gus, but for more information, please follow us on LinkedIn or check out our website where we regularly post updates at an industry level. Thank you.
Great. Thank you, Margie, and thank you all. Firstly, I'd like to start by also acknowledging that I'm part of a very big team here at the HILT CRC and Adelaide University, and hence some of the co-contributors are listed here. I'm going to give a bit of a technical overview of this challenge and opportunity that Margie has given a good introduction to. So Margie mentioned electrification is one of the important opportunities, and that's also one that our industry partners are focused on. So this is just highlighting the picture on the left shows the mix of primary energy sources across the globe on average that are used in the alumina refining process. So you can see predominantly we've got fossil fuels being burnt, and Margie mentioned natural gas is typically used in the calciner, and both energy sources are used for the steam making process. So the key point is, if we look to the right, this figure shows that the average price of energy, if you just look at if we were going to directly replace the heat with electricity, it's going to cost more. And this is because typically, historically, electricity has been manufactured from heat by burning fossil fuels with efficiency of typically somewhere around 40 to 50% thereabouts. So if we're just going to simply do a direct replacement with current technology, it's simply putting heat by resistive heating, it's going to cost more. So that means we need innovation. Also, there are other options, and this shows that compared with electricity, some of these alternatives, and Margie already mentioned things like biomass, although they're more expensive also than fossil fuels, they also can be relatively cost effective with electricity. So there's a number of all these options we're looking at in the HILT CRC, but just to summarise those barriers and enablers, the key point is that there's an economic barrier. If we're simply going to do a one-to-one replacement of the current energy sources with the alternatives, we're going to add to cost compared to unmitigated fossil fuels. So this means we have to harness the opportunities of how to both improve performance. So we don't just need to electrify, but we need to electrify in ways that improve efficiency. And also, although electricity on average is more expensive, during intermittently it can be lower cost, but to harness that we need to find ways to integrate the intermittent sources, which is why Margie also highlighted opportunities for things like thermal storage, which is also one of the opportunities. Of course, there are others such as alternative fuels and hybrid pathways that are also prospective, and we need to look at all of those. In addition to those economic barriers, the technical barriers, that these technologies are not yet commercially available, and there's also market barriers and opportunities as well that I won't go into today. So one of the key enablers that we're looking at is, in terms of efficiency, is how to do better with circularity, and this is to recover things that are currently wasted and vented. So just to highlight this example, currently the digestion process is what is used to purify or separate the hydrate in the alumina from the impurities in the ore, and this is currently done with steam. So currently we make that steam by burning fuel and air, and the steam then goes through this process and is vented. On the other hand, in our calcination reactor, it turns out that the hydrate ore or the bauxite is actually got steam chemically bound to the hydrate. And this is currently also vented at the outlet of our calcination reactor. So what we'd like to do is close this loop and do it more efficiently. We'd like to capture this steam that's released from the calcination process and bring it back to do this digestion in a way that then avoids having to burn as much fuel or use as much electricity in this make-up process. So this is the kind of circularity opportunity that we're looking at trying to harness in the HILT process, and there's a whole lot of elements to that. But Saul will go into some of those in more detail. But of course, changing the alumina process, it's a very complex industrial process, and it doesn't happen in a single step and doesn't happen overnight. So this shows the two main energy sources. On the one hand, we use fossil fuels to make steam in some kind of steam generator, and that goes through this Bayer process, and we also put fossil energy into the calciners. And one of the things we're evaluating in the HILT CRC is the various steps in the industry transformation that will involve progressively changing from this 100% fossil fuel utilisation in steps where we gradually start replacing maybe some e-boilers in the first step, and then through to recovery of steam in mechanical vapor recompression and other progressive steps in changes in the industry process until we get to net zero. So what we've been doing in the HILT CRC is developing some estimates of the timelines of what some of these technologies might be available in consultation with our industry partners to develop understanding of how the different energy requirements will be made and what the technology steps will be needed to go through this transition from where we are today through to 2050. So we can analyse how much energy would be required and what the economic costs of those would be. And the key point you see from this, on this diagram, we're showing the energy requirements by current refining. And you'll see that in this case, these blue lines are fossil fuel utilisation. Then we've got imported electricity. And you'll see that in this particular scenario, which is based on this diagram we saw here, because we can recover some of the steam that's currently vented and bring it back to displace the steam that's currently manufactured in the boilers through burning fossil fuels. This means that the net energy consumption to 2050 can potentially be reduced significantly. Depending on the scenario, some 30%, in this case is around about a 30% reduction, more is possible, and we're looking at what those different options look like. So this provides an important mechanism to offset the otherwise higher cost of electrification. And this is made possible because we're not burning fossil fuels and diluting that steam with combustion products. So that gives us an economic opportunity, one of the ones you want to harness. The other one is things like integrating variability such as the thermal energy storage options that I won't go into in detail today. So to give you an example of the economics, I won't go into this in detail, but we model all of those different steps in the process in detail, and these can be modelled economically, firstly with a process model, and then the economics can be accounted for. And here you can see this is one of the systems that can be used to recover steam from that calciner process. There's a cleanup system, and there's also a series of compression stages. These are more efficient than using boilers to do it without going into the details. So the key point is that by modelling those, you can see that one of these scenarios gives a break-even cost, shown in this red line, of approximately some 60 or so US dollars per megawatt hour, which is about the same as the average price of electricity when you convert US dollars to Australian dollars. So this doesn't mean that the system is economic, because of course there's lots of this is preliminary analysis, but what it does do is it shows the opportunities that can be made if we start doing smarter things than simply just doing one-for-one replacement by doing greater circularity and efficiency. So to summarise the key points of what we're looking at in the HILT CRC is we see that we need to make this transition economically attractive. We need innovation to enable this transition to net zero to be done economically. We need both innovative technology. Part of that is in this increased process efficiency that I mentioned, together with things like the flexibility and circularity. Some of the technology platforms I didn't go into in detail, but they were illustrated, and Saul will talk a bit more. But this is mechanical vapor recompression, thermal storage. There's also alternative fuels. But then to do this, we need to look at the whole system, prospective systems, and this includes the alternative steam generation routes. There still will be some make-up steam required. We need the steam recovery paths that I mentioned, and also the flexibility. But this needs to be supported by fundamental research, because these new reactors and systems will be operating in different environments. So we need to do the fundamental research to de-risk the process of introducing these new technologies, which, whilst they're already in development, they're still not yet commercially available. And this also needs advanced measurements and the kind of scenario analysis that I talked about to evaluate the different economics is also a part of what's needed to help inform industry, but also inform government and to plan for the kind of additional energy infrastructure that Margie referred to. Obviously, if we can reduce total demand, it can make those kind of things potentially more perspective. So thank you. I'm going to stop sharing and hand over to Saw to talk about some of the details of what's been undertaken in the AlumiNEXT project.
Thank you, Gus. I hope everyone can hear me clearly. Is it sounds okay? All right. Thanks, Gus. Thank you, Maggie, for the introduction. So, I think what I'll be presenting over the next 15 minutes, literally, will be focusing on what Maggie mentioned about within the fence of the refinery. I think it's great to literally acknowledge my research team over here, and as well as our industry partners, who literally put a lot of support into this particular project. Which I'm going to provide a bit more in depth about what are the things that we have looked at. So in terms of the overview, just quickly going through AIM project teams, and the most critical one will be the work package overview. And then after that, I'll give a short update in terms of our drop tube reactor, and then we'll be wrapping up with the summary and the next steps. I think it's good to really coming back to AlumiNEXT. So I think over the last couple of months, we've been refining our aims, our research direction. So I kind of put together a quick kind of sentence about what exactly we are focusing on. So as Gus already highlighted in his presentation slide, so we are literally focusing on the fundamental science. There's quite a bit of process modeling involved in this particular program. And then certainly in this case, we're also looking at the new calciner design to accelerate the transition to net zero alumina production. So here we are focusing on from the atomic scale to the industrial scale. So I think I can elaborate more in the upcoming slides. So in terms of the aim, I guess this is something that we still holding it as what I presented previously. But just to literally give a bit of introductions that we have divided into two work packages. So one is focusing on the steam generation and recovery, and then the work package 2 is predominantly focusing on the alumina calcination. All right, so this are our literally research teams and also our industry partners. So we had our face-to-face meeting back in 2025, and then we had one recently 2026 in a couple of months ago. So really, as I mentioned, I really wanted to acknowledge the contribution from the research team and as well as our industry partners. Yeah, so literally without going too much detail, so this particular slide is literally focusing a lot on the different activities under work package 1, as I mentioned before. So we have divided into two kind of sub tasks. One is focusing on the system modeling, and then the other one is focusing on process modeling. So we have two industry partners, or our partners is literally providing quite a lot of support from, especially for the SysCAD modeling and also the Plexus establishment of the model. And then when it comes to the fundamentals, so we got about 3 to 4 activities happening, undertaken by our research students. So focusing on kinetic studies of steam calcination, physical properties of alumina, physiochemical properties of alumina. I'll elaborate more further in the upcoming slide. And then there's another program that's focusing on reactor upscaling. So we got one student that's looking at particle fluid dynamics, another student's focusing on CFD modeling, and then the last one is looking at the next generation alumina calcination process. So probably I'll just jump quickly into the work package overview. So within work package 1, so as I highlighted before, that we are focusing on steam generation and steam recovery. So I think you already heard quite a lot from Margie and Gus about high energy use, especially for the steam generation. As a result, because we are using fossil fuel, that's why you see that there's a relatively high CO2 emissions generated during the steam production. So within this work package 1, we got kind of like 4 sub or 5 activities. So one is focusing on steam generation. So the question is all coming around that how to decarbonize steam supply. So we looking at the moment, obviously we are still modeling the existing steam generation through natural gas combustion, coal combustion, but then we are also looking at some of the electrification that I think Margie mentioned early on about e-boilers, TES, and then we do establish quite a number of models, as I highlighted before, using Plexus to better understand how we can literally optimize the cost and the load. So I can come back to this shortly. And then whereas the other program that we are focusing on is the waste heat recovery. So in this particular activities, we are looking at the opportunity for waste heat recovery. So we are looking at MVR, mechanical vapor recompression, thermal vapor recompression, heat pumps, or the hybrid of some of the technologies that I highlighted before. More recently, we also started to look at the water balance. So it's really important that, when you do this sort of heat recovery, how is it going to influence or impact on the water balance? So this is something that currently one of the researcher is looking at the water balance model. And then literally we will provide a bit more information in the upcoming updates in the future. And then the last one is looking at this advanced compressed air energy storage system. So we are looking at some other opportunity where how potentially compressed air store can power both electricity, or provide both electricity and also heat for steam generation. So there's a model literally will be generated from that particular work. And then overall, once you put that together, so those information will be fed into this optimization framework where we use Plexus model to literally perform the cost and load optimization. And then last, literally what actually we want is to provide this sort of like flexible steam supply and also the decarbonized steam. So let me quickly go to the next slide. So this is the kind of the activities that I think Gus already highlighted before without going too much detail. So certainly I would like to highlight that we do have literally a quite comprehensive SysCAD process simulation of all the Bayer process and also the calcination. So really appreciate the support that's provided by the SysCAD team. And then certainly I think Gus already highlight in terms of the modeling framework about how we can provide the cost optimization and the load. So without going into details because of the time constraint, so I just highlight the bits and the pieces that we kind of put together, how we can come up with this HILT or AlumiNEXT system modeling framework. And then the next part is now we're moving into the work package 2, which is the next generation alumina calcination. So within this particular research program, as I highlighted before, that we are focusing a lot on the fundamental research, especially we want to understand, how the calcination temperature and atmosphere will impact on, some of the alumina transformation. So here we got a PhD student that's focusing on the product quality and kinetics database for this particular activities. And then there's another student that's focusing more onto the what drives particle breakage. This is an important question about, especially is to do with the U. So the higher the particle breakage, obviously that would also reduce the U, and also will influence the downstream processes, especially for the aluminum smelting process. And then we also started to look at from the atomic level or molecule level, like how do these OH bonds breaks during calcination. So as Gus highlighted before, that during the alumina calcination, you do have this sort of like aluminum trihydrate decompose into alumina, and then it releases 3 moles of water. So something is, yes, we can measure the weight loss changes during the transformation, but there are some mechanisms that cannot be measured through TGA, SEM, that sort of system. So therefore, that's why we are having what do you call a modeling, this is molecular dynamic simulation to model that particular mechanism. And then moving to the modeling side, so we have a number of PhD students undertaking some different activities. So one is how do particles flow in a calciner. So we have students that's looking at isothermal studies as well as a CFD model to better understand some of the particle gas interaction. And then we do have students that's focusing on more onto retrofitting. So it's like hydrogen or syngas ready for existing calciner. So we are doing quite a lot of work how we can retrofit by changing or fuel switching from natural gas into either hydrogen or syngas. So there's a model developed through that particular studies. And then last but not least, so we do have this potential energy saving from the steam recovery that are highlighted in the previous work package, especially when you do steam calcination. There's a huge opportunity where we can recover the steam from the calcination process so that we can reduce the energy consumption in the Bayer process. And then the most important one is the new development. So literally what we are trying to do is to learn from those fundamental science to design our new calciner. So it's something that's already undertaken by one of the PhD students to look at this particular question. So overall, in terms of the outcome, so certainly we still talk about how we can transition from existing calcination process into low carbon. So therefore, that's why we are trying to reduce the energy and CO2 reduction. But also we do have another program that's focusing more onto the next generation calciner. All right, so this is the kind of like overview because of the time constraint. So I can't really go into the details of each individual component. So, but I kind of like summarizing a lot of the fundamental research work that we are looking at, the lab scale reactor that we are talking about previously. So when you look at this particular drop tube, which is the middle of the pictures here, is giving us a lot of the different avenue of looking at the particle breakage, which is shown here. And then we are looking at this molecular dynamic simulation to look at the OH bond breaking. And then we do have some other CFD that's looking at the particle flow of the system. And then we currently looking at some of the energy balance of this electric calciner, which we heard a bit more about. We are trying to electrify some of the calcination process. So we are starting to kind of better understand how we can put our effort into the particular process that we wanted to focus on. I'm just conscious with the time. So now I'll just quickly go through the drop tube reactor updates. Really, I mean, why we need this particular reactor? So it's really giving us this to understand how this net zero atmosphere, how it will affect the calcination performance and product quality. So as we kind of move into electrification pathway, we get to kind of like literally tune the conditions that we probably might not be able to do that when we do the conventional case, like burning natural gas, because usually we'll have the water, the CO2. Whereas for electrification, you can tune it whether you want it to be steam calcination or dry. So why it's important? So certainly here we are trying to generate the kinetics, mass, and heat transport data to validate and inform our literally the next generation calcination process. And then within this drop tube system, we will be able to control the atmosphere, the temperature, the residence time. And then obviously this will enable us to do the different systematic studies of looking at the steam concentration, particle size, and also the temperature range. So importantly, the results that we are getting from this drop tube reactor will be like directly scalable, because the work or the design that we base on is looking at the dimensionless number that we are trying to match with the industrial operating regime. So this experimental data will be able to validate the model for our, literally the next pilot scale that we like to focus, which is after the AlumiNEXT, some of the work that we are currently undertaking. Without going through too much detail, so as I kind of mentioned before, that these are the dimensionless number that we're trying to identify the right reaction in the flow regime. So as we highlighted, that we are based on the dimension numbers of the Reynolds number and the Dam column number. So without going into too much detail, so certainly these are the regime that we have highlighted based on some of the industrial scale system. And this is where we're going to focus a lot of our operating regime in this the green box. So in terms of where we are up to, so we have literally like this work has been done like for many months. So we started with this safety review team. So we go through the P&ID review. We have completed our hazard workshop. Now we are in the phase of the procurement, fabrication, and assembling. The slide that's showing literally next is just to give you a bit of quick glimpse of like we have constructed, installed the frame reactor, and then we got the furnaces ready to be integrated into the frame, as well as the drop tube reactor body and components. So we are almost like literally, I'll say that nearly there. So we probably a month and a half away from commissioning. So the team is working really hard behind the scenes, trying to put everything together. So in terms of summary, I guess I just wanted to wrap it up. So we have done quite a bit of steam generation. Literally, we already looking at this particular optimization framework. So it's already in the process of literally establishing this particular framework. I think the research team has done quite a lot of like different heat recovery pathway, and we have models. Some of the configuration as Gus already presented early on. There are some work being currently undertaken in terms of the interim calcination kinetics and particle breakage data. So we're using our existing reactor facilities while waiting for the drop tube reactor to be completed. And then, as I mentioned early on, that the drop tube reactor is under construction. So what's next? So I think commissioning is the one that we're going to prioritize over the next couple months. Then after that, there will be quite a bit of work to be literally generated in terms of the kinetics and breakage model, water balance, process modeling, and then I think lastly is the electric calciner prototype development. So again, because of the time constraint, so I won't be able to go into the details of each individual research project. So, but certainly there will be another opportunity where I'll be able to invite some of the researchers to provide a bit more information about some of the specific tasks that are highlighted here in this particular presentation. So thank you again for your time, and I'll kind of pass it on to Emilio, who is the last speaker of the this particular webinar. Over to you, Emilio.
Thank you, Saw. Thank you, everybody. So before I start, last webinar that I presented multiple options for decarbonization concepts, all of them, one better than the other, one more expensive than the other. And it's time now to narrow down the, it's time now to narrow down the options to one or two bankable alternatives. The pathway for the decarbonization is much clearer now, I would say, but still challenging, dynamic, and also urgent. The topic I was invited to present today is updates on current status and priorities for alumina decarbonization. And the focus is on alumina, not in aluminium, and technical. It's important to say that it's difficult for us to predict what will happen with complete confidence in the future. But what we can do is based on is making informed decisions on the best available evidences that we have and prepare for all possibilities that we have. And this is more or less the basis of what I'm going to present today. The key point that is important to start is what are the decarbonization triggers for EGA. So we have here corporate and national targets, we have client expectations, and we have potential expansions of CBAM to the refinery in the future. So when you look at this timeline that is presented here in this slide, right now in 2026 and 2027, we have direct costs due to the, because we have sales in the marketing in Europe and UK. There is some carbon implications there, costs implications. In 2030, EJ made a public announcement and commitment based on calculated information, solid information, a 25% intensity reduction in scope 1, 2, and 3 emission. Okay, we also have ASI targets here. There is some other challenges for us to go on that. But for the refinery 2031, we have the CBAM phase 2, which is what they call scope 3 emission, which is alumina. So directly emission will be impacted here for the business, of course. We also have in 2035 the UAE targets from the National Determined Contribution Program from the government, 47% absolute emission. This is not intensity. So this is different from the previous targets. We also have 64% in 2040, and EGA also have a commitment for net zero by 2050. Okay. So as you can see here, we have a time for us to complete. Okay, it's not a lot of time, and we needed to work really with good focus on these items here. In terms of our refinery decarbonization, we are working with 3 horizons. With focus on the near-term solutions that are proven. So we have here from 2026 to 30, we work on what is proven, what is available, what we can make strong commitments. 2031 to 24, we needed to deal with the hard-to-abate areas, okay? And finally, the rest 2041 to 2050 is any residual that we needed to catch up to reach the net zero. So starting with the proven solutions, what we have here is the steam decarbonizations. So our intention here is to switch from natural gas to preferentially solar and thermal energy storage solutions for the steam generation. UAE has a lot of sun. We have a lot of the biodiversity of the country is very favorable for solar energy for us. As such, we will try to explore this option, and this will be one of the main positive options we have there. Okay. In parallel to that, power decarbonization will also be together with this, exploring renewable energy there. And we are looking at our refinery, we consume a lot of diesel as well for transportation, for equipment management. And the intention is to switch the diesel trucks to electrical vehicles trucks, mainly for both site residue transportation, but also for other duties or in steps. On the hard to abate area, we have here two important items. One is explore waste heat recovery, mainly from smelter and the refinery and the calcination, and also work together with HILT CRC and our colleagues, collaborators from other industries to develop a new calciner technology. Okay. So we have here in our portfolio of strategy to continue with focus on R&D for the calciner decarbonization so that we can have a better selection, a best selection of the alternative. In terms of electrical truck, so currently we are exploring electrical vehicles for the transportation. So we are in the stage to do a pilot of electrical trucks. In this pilot, we will evaluate the charging time, the turnaround, the efficiency of the batteries. We will explore swappable batteries to ensure we operate at optimize the arrangement. And based on that, we have a plan to renew the entire fleet. Based on the success of the pilot, replace the entire fleet. In addition to that, the intention also is to develop a solar photovoltaic microgrid in the rehabilitated bauxite residue areas to source this energy for the trucks. So this is a combination of a value added to a residue area rehabilitated in generating value for renewable energy to be used and reducing diesel consumption. The other priority we have is focus on the decarbonization of steam for the refinery. And as I mentioned, we are concentrated in a few options. Here, one of the options is solar, bringing electrons to the plant and then store somehow in a thermal battery storage. But also we have the option, challenging option to bring using parabolic solar to produce directly steam and transport to the plant. The second option is the challenge is that the area needs to be distant from the refinery. So it's a long distance transportation of steam. But both options we are evaluating to see which one has the lowest risk and the most feasibility arrangement for this. But basically, with the heat, we will generate the steam for the refinery. In parallel to that, we are exploring waste heat from smelter. So we have multiple pots in the smelter. Each of them, normally they have a waste heat from that they needed to do. And we are exploring to capture this waste heat and bring to the refinery in a combination with the renewables. Okay. For the calcination, this is one area that we consider the most critical and most difficult to do. We have done a lot of work understanding how to retrofit or partially decarbonize the calcination. So we started looking at a simple solution. Let's include a heater in one point of the process and inject electricity to the calciner, as you can see in this illustration here of our calciner. So the cost of this electrical heater is affordable for a 15% reduction in the decarbonization, in the abatement in this calciner. But when we look at the details, and on the right side of the picture, it's a very big heater. So you have a refractory, you have a big load. You need to look at platforms. You need to look at the basis of it. You need to consider that you are installing a large equipment in a calciner that is alive. It's producing alumina. So there are multiple complications of it. And the cost can be sometimes 10 to 15 times more than the cost of the equipment. So it's a relatively high cost. It's still in evaluation that we are doing. But this comes to a point then why not potentially to go to a new calciner, something more simple a new development that has multiple choices, options, so that we are now also in parallel looking at a new generation of calciner is a development, of course, together with HILT CRC. HILT CRC is vital to support us in this development. But if I give share a little bit of vision or expectation, what we could offer as advantage, understand that any new development we need to have a compelling business case. So what I'm sharing to you is more expectation issues, but we believe we could have something similar that could fit in this new concept. But the idea here, we should have a calciner that have zero combustion, so it completely eliminate all the burner management system, all excess air and controls associated with it. We would like a calciner that has emission-free, of course. We want to reduce the CO2 to zero. But on a calciner, we also need to look at NOx, SOx, much less particulate emissions as well. Okay. We need to look at, in the new calciner, the quality of the alumina needs to the starting point needs to be exactly the same quality of the alumina. But why not to have a better quality alumina? Why not, for example, to minimize breakdowns in the calciner? Why not to minimize alpha alumina? So these are some questions that we can give in challenging the group when we design any new calciner. This new calciner needs to have better energy efficiency, definitely. If we are going to use renewable energy, if we are going to use any other source of energy, if you're going to use more capital, you need more efficiency. This new calciner preferences for heat export and steam export. If there is steam available, if there is heat available from the reaction, from the endothermic reaction of this calciner, why not to use this steam in the plant? It makes a lot of sense and very well aligned with HILT CRC goals as well. Calciner is a source of water for the refineries. Sometimes people don't give them too much attention, but this is becoming much, much more important. Okay, water, calciners generate water in the stack. Why not to capture this water and bring to the refinery so we can minimize the consumption of water that is required to operate this plant? We would like a calciner that has lower footprint. It needs to be more compact and much more simple. Sometimes it's more difficult to make things simple, but we need to think about how to make it simple. We should always look at the simple options in terms of CapEx, OpEx. Okay? And also this calciner needs to be thermal energy storage friendly, at least for our concept of using solar. The solar battery, it needs to have compatibility. Finally, one thing that this calciner doesn't have, of course, is the maturity. And that's why there is a lot of work to understand. There is a lot of good collaboration from different expertise around the world. But if we can at least achieve most of these items, I don't believe we achieve all of them, but most, certainly we will be much more successful in defining this new calciner. Okay, that's it for me. Back to you, Rochelle.
Brilliant, thanks, Emilio. So we don't actually have any questions. So the team have obviously done the most wonderful job of explaining everything with perfect clarity. But I think what we can reflect on is the power the AlumiNEXT project and the collaboration is bringing through HILT is the ability for industry to really articulate not just what their challenges are, but what does the ideal solution or that lighthouse look like, which is what Emilio's just done for us. And if we don't set that lighthouse, we'll come up with solutions, but are they really giving us the step change? So it's great to have that collaboration, and the industry input and technical expertise in conjunction with the research is certainly what will give us these new solutions. And they do have to be pragmatic, feasible, and importantly, implementable in a brownfields environment, which is where a lot of our refineries are. So in light of the time and the fact that many of you have got other work to get off to, I'd like to, on behalf of the HILT team, thank our four presenters, Margie, Gus, Saw, and Emilio, for giving up their time and presenting for everyone today. And thank you all for your attendance, the 100+ people we've had online. That's very much appreciated. We like to share our knowledge broadly. And if you do have any specific questions, I'm sure our wonderful panel of speakers would be happy if you reached out direct, and look forward to seeing you on another webinar very soon. Thanks and have a good afternoon, everyone. Bye.